There we go. So now we're recording. Very good indeed.
Yeah.
Because by the time I get to get past the usual stuff, my mind is already set on, let's talk about memory stuff. It's really cool. It's really something that we haven't seen before. Okay, so we will label these. One is S, and the other one is R. And then we have two output pins. According to the notes here, we have two output pins, Q and NQ. So we're going to put one here. Now, obviously, if you were to do this the first time, you wouldn't know where to put the pins. Okay, so you might end up having to rearrange things a little bit. But the idea is this. Okay, the idea is we are really just specifying the objects here. There we go. So are we still doing okay so far, corresponding the picture, the diagram of the circuit with the so-called pseudo C++ code? Okay. So NAND2, input pin, output pin, those are classes. They're used to stamp out actual objects, just like we would use things inside LogicSim to create actual components. So now we go to circuit.addNode, So it is probably a good idea to explain what a node is. A node in electronics, in circuit design, is really just a conductor connecting multiple points electrically. So logically, if this pin or this part of this thing is connected to that one, connected to that one, it is a single node. So when I use this kind of pseudocode here to say add node, okay, the new node thing is really just to conform to C++ terminology so that we know that we are adding a new node object into the circuit. What is really important part, the really important part is really just whatever is inside the most nested portion of the parentheses. What are we connecting? Okay, a lot of times we're only connecting two things, but sometimes we're connecting 3, even 4 things at the same time. So in this case, all we're trying to do is to connect the pin of the input pin S to the input, one of the inputs of N1. Okay, and I use the array indexing mechanism to differentiate which one we are connecting to when we have multiple inputs. Is that okay? So what this is doing is just doing this. The next one is doing this. And then this one is kind of interesting because now you're looking at this and go like, oh, we are connecting 3 ports. We are connecting Q.pin. That's supposed to be Q.pin, not Q common pin. But we are connecting the pin Q to the output of N1. That part is relatively easy. But at the same time, we also want this node to connect to the other input of N2, which is this one here. In other words, we are tapping it here, and we are connecting it back here. So far, there's no loop yet, okay? But the next step will give us a loop. So the last step is to connect the output of N2 to the input of N1, and also to the output pin NQ. So that would be going from this pin to this pin here, but also going back to here. Aha! So now we have an interesting circuit, because this is the first time we see a circuit that has quote-unquote a loop in it. Okay, the output of one gate serves as the input of another gate, but the output of the second gate would also serve as the input of the first gate. So we have a little crisscrossing now. Is that okay? And I claim that this is the first memory device of this entire class. It's made out of 2 NAND2 gates. What kind of memory are we talking about? Okay, so let's take a look at this circuit here. Okay, we'll take a look at the graphical representation, but I'm going to turn off simulation. And let's see, can we not display the state of the pins? Reset. Okay, there we go. Okay, this is good, because I don't want the ones and the zeros to confuse in our analysis of this thing. Okay, so when you look at N1 and N2, they are NAND gates. is there a particular output that can be guaranteed given that the input of one of the pins is a certain state? In other words, we want to lock down things that we know for sure. If you turn this input pin blah, this gate will output blah blah, okay, regardless of what the rest of the circuit is doing. Yep?
No, wait for just one pin?
Yep, just one pin. Is there a particular value of one pin that can guarantee the output to be a particular state, regardless of the state of the other pin? Yep?
If you leave one pin as 0.
Yep, you got it. Okay, because it's a NAND 2, which means it is the negation of an AND. When you're looking at AND, okay, if at least one side of an AND is a false, the output is guaranteed to be false. Okay, it doesn't matter what the other pin is saying. Is that okay? Well, this is not exactly AND, it is NAND, which means if one of the input pins is guaranteed a 0, the output of the gate is guaranteed a 1. Is that okay? Okay, so that's one way we can analyze and say that if S is a 0, then Q is guaranteed a 1. Okay, that's regardless of what R is. When R is a 0, NQ is guaranteed to be a 1 as well. Okay, so now we can try to make a truth table. So I'll switch to the document camera. Let me make it happen first. Okay, so the situation that we have here is that we have two NAND 2 gates. We got N1 and N2. We have one input pin called S, one input pin called R, one output pin called Q, and one output pin called NQ. And it goes like this. This one goes here, this one goes here, and then there's the crisscrossing right there. And another crisscrossing like this. So this is the circuit that we are looking at. I'm reproducing the circuit here so that when we talk about the truth table, I don't have to flip-flop between the two. Okay, so let's go take a look at the truth table. S and R are input pins. They are independent, so they become the independent variables of the truth table. And then the output would be Q and NQ, so they appear on the other side. So naturally, we have 0, 0 as the input, 0, 1 as another input, 1, 0 as another input, 1, 1 as another input, like so. So what we'll do is we're going to take a look and say, when S is 0, this NAND 2 gate is going to output a 1 regardless. That means Q is always going to be a 1. When R is 0, this NAND 2 gate N2 will always output a 1, so the NQ is guaranteed to be a 1. Is that a part okay? Is the first row of the table doing okay with you? Okay. Let's take a look at the second one. The second one has S being 0, R being a 1. Once again, when S is a 0, N1 is guaranteed to output a 1, so Q is guaranteed to be a 1. What about the other one? What about NQ? Let's look at NQ. So when Q is getting a 1, this wire is getting a 1, R is a 1 as well, so we have 1, 1 as input into N2. This is a NAND 2 gate. When both inputs are 1s, the output is going to be a 0, like so. Is that okay? The third one is symmetric to the second one. It's just exchanging. So when R is a 0, NQ is guaranteed a 1. Okay? But when NQ is 1, this node is also a 1, so we have a 1 going into the second input of N1. But we also say that S itself is 1, so now we have 1, 1 going into N1. And because N1 is a NAND 2 gate, the output is going to be a 0. So the third row is completely deterministic as well. The last one is a little bit tricky because all we are saying is S is 1, R is 1, right? Well, but then it depends on the other pin to determine the state. Does that make any sense? So now you have to look at this case and go like, oh, this is a little bit tricky. Because when S and R are both 1s, then if Q is a 0 to begin with, then Q will continue to be a 0, but this 0 will go into here and make NQ equal to 1. On the other hand, if NQ was a 0 to begin with, before you get to the 1, 1 of SR, if NQ is a 0, this wire will also be a 0 going back into N1. Well, that would make Q guaranteed to be a 1. So the only thing you can guarantee is that N and NQ are opposites of each other. But which one is a 1 and which one is a 0? We don't know. Yep, go ahead.
And so you're saying, so it just depends on the state of the output pins.
Yep.
Based on the previous, whichever combination you did.
Yep. So that means if the 1, 1 configuration is preceded by one of the 2 middle rows, it would just retain that. Okay, let me say that one more time. If you perform, okay, let me name these sequences. So this is A, this is A1, A2, and this is B. So if the sequence is A1 and then a B, that means it will retain the state Q is going to be 1 and Q is going to be a 0. On the other hand, if your sequence is going from A2 to B, then Q is guaranteed to be a 0 and NQ is guaranteed to be a 1. Is that okay? But that's really kind of interesting. We have never seen a circuit like this in this class up to this moment, where the inputs are exactly the same, S and R both being 1s, but the output of the device depends on what it was before. Is that okay? So how do we call this capability of, oh, it will be whatever it was before? It's the simplest form of memory. It is a form of memory. It is very crude. It doesn't seem very useful, but nonetheless, it is remembering what it was. Is that okay?
So this is essentially 1 bit of RAM.
Not
or
quite.
2 bits
Okay?
of RAM.
It is not that useful because there's no, you cannot specify whether you want to store a 1 or a 0. There's no one single pin to say that here's a 1, remember it. Okay? It doesn't say that. It has, the 2 pins have a different way of looking at things. By the way, the term S is set, R is reset. Okay? And they're active low, which means when the input is low, that function is active. Okay, let me say that one more time. S and R as input are active low signals, which means when the signal is a 1, it is inactive. When the signal is a 0, then it is active. We are saying, oh, let's do that. So when S is a 0, it means, yes, let's go ahead and set the SR latch. When R is a 0, it is saying, let's go ahead and reset the SR latch. When they're both 1s, you're doing neither. You're not setting, you're not resetting, you're just saying, maintain whatever state it was in. Just keep it that way. Is that okay? Yep, go ahead.
So you're saying for B, to get Q and NQ, it relies totally on A1 or A2?
That is correct.
What about A0?
Ah, that's a very good question. So what if you start with A0? So you have A0, okay, let's name this one A0. A0 to B, what is going to happen here? What do you think? It cannot retain 1, 1. There's no way it can retain 1, 1. So what do you think it's going to do? Let's think about it in a lopsided way. In other words, we'll make one gate really slow and the other gate really fast and see what happens. Okay. So that's a very good question. So we'll look at this gate here, and we'll say slow N1, and we have a fast N2. Because if they're about the same speed, it is not easy to analyze. But when you say, oh, one is really fast and the other one is really slow, then we can actually make a timing diagram and figure out what is going to happen here. So the next thing we want to do is to look at a timing diagram. Okay, so a timing diagram looks like this. We're looking at a timeline, and we have S, R, Q, and NQ here. So each one is representing a line that indicates something. So the first condition is A0. A0 is having 0 for S and 0 for R. So S is low, R is low. Okay? And I can use a ruler to kind of draw the baseline and use a different kind of color to indicate the baseline of each one. So I'm just drawing a line here. This is 0, 0, 0, and 0. This is called a timing diagram. It's really kind of fun. All right. So let's say we change S and R both to 1s simultaneously. But before that, we know Q and NQ are 1s because of NAND gates. Is that okay? Does everybody understand the diagram, the timing diagram? Time goes from left to right just like a usual timeline. So this is the initial condition. This is basically A0. Okay, so if we want to label this section of the timeline, this is A0. So at the end of A0, we decide that we want to change both S and R to 1s at the same time. Right? So that is instantaneous. This goes to here, this goes to here instantaneously. That's not a problem. And we also say that N1 is slow and N2 is fast, which means N1 responds to input changes instantaneously, and N2 is kind of like, I'll take some time to figure it out. Is that okay? Yep, go ahead.
Opposite, right? N1 is slow, N2 is fast.
Right, so at this point, after this transition, then N1 is the fast one, right? So N1 will still be seeing a 0 coming out of N2 because N2 is slow. So we'll have a 0 going here, and then S, this would be changed to a 1 immediately. So that means S will continue with, that means Q will continue with its high output because N2 is slow.
I'm not sure if it matters, but you have it the other way around on the paper.
Oh, slow N1. Oh, darn it. Okay. Okay, so if N1 is slow, that means this will continue. So that means NQ will continue to be a high signal. If NQ is high, S is already a 1, then this is going to be a 0. So that means Q will drop to a 0, while this thing is still a 1, because it is slow. Okay? And at this point, what's going to happen next? Will it settle, or do you think it's going to go between those two states? Okay, Q is already low. So Q being low, we go back to N2. R is high. But if one side is low, the output is going to be a 1. So it will continue to be a 1. So we don't have a problem. But if it's a propagational delay thing, that means whatever is seen by this gate will have a reaction later. Okay? So that means the transition of S going high is only going to have an effect later on. But this signal continues to be, okay, hold on. This signal was a because look, we're looking at a Q here. So we are looking at this signal NQ was a high, S changed to a high at a later time. Okay, I'm getting myself confused here. But this circuit is supposed to oscillate. It will go between the states. It has to do with the reaction time of the two gates are slightly different. So one will basically, respond a little bit later, but because of that, it is just delaying the effect of the change. It is not responding to the change, it's just being slow. Is that making any sense? Okay, let me see if I can figure this out. So N1 is slow, so that means it's responding to the changes slower. So N1 is this one. Okay, I need to label the output pin so this way it's easier for me to see which one is which one. So N1 is the slow one, which means it's going to respond, and the inputs are N, Q, and S. Okay, so respond to this change, which means it's going to continue to go, it will continue to be high. NQ is the fast one to respond because its N2 is faster. So this one will see the change from R quicker, and then the other one is a 1 already. So that's why N2 is the one that will change first. When this changes, and this one is responding slower, okay, but this change is going to trigger a change here. This change is going to trigger a change here, which they basically just leapfrog each other. So they will actually oscillate. Is that okay? All right. Which is not good. Anything that oscillates in an electronic circuit is not a good thing.
Alternating current? Is alternating current like the Johnson?
Well, it becomes, but if you have no control over the frequency, then it serves no purpose. If you have control over the frequency, then it's not a bad thing. Yep.
So this would only be efficient for A0, A1, and A2, alpha B?
Yep, so if you want to go to B, everything may start with A0, but A0 has to go through A1 first or A2 first before going to B. Going directly from A0 to B is not a good thing, because the result either is undetermined, you don't know which one is going to be a 1, or it will even be worse, which is oscillating. And I think the new version of Logisim can actually detect oscillation, but the old version, the one that we use, does not do that. Are we doing okay so far with this circuit? So the important part to remember is there's no change here. If you focus on these 3 rows, we are good. If you go from A1 to B, it remembers the configuration of A1. If you go from A2 to B, it remembers the configuration of A2. Are we doing okay so far with the SR latch? Okay, we're good. Okay, going back to the notes, on this, over here. This is a text analysis of what happens and why we have this part here. NC stands for no change. So this is kind of the table that we saw earlier. And then we start to get into a D flip-flop. So we'll try this 2 more times to construct a circuit diagram from looking at the text version. So let's see, new page. All right. So we look at this one and go like, okay, so what are we using here? Oh, we're using an SR latch already, and then we have a negation gate N, we have two NAND 2 gates, which is N1 and N2, and then we have two output pins, Q and NQ, just like usual, and then we have 3 nodes. Okay, so let's go ahead and use LogicSim to construct the circuit first, and we'll add this circuit as a D flip-flop. Okay, so we'll go ahead and make a circuit out of the SR latch, okay, which is, I think this is good. We just have to label the individual pins correctly. S, R, and then we got Q and NQ. I'm going to use the proper notation here in electronic documentation. The slash is basically negation or active low. So what this is saying is we are saying that the set signal is active low, so is the reset signal. When that particular signal is a high or 1, it means don't do anything, we are not going to set or reset anything. If one of them goes low, it means we are either setting or we are resetting. Whichever one goes low is the function that we're activating. Q is non-negated as an output, so it's by itself. Slash Q means not Q. That's basically all it says. Okay, so Q and not Q are usually opposites of each other, with the only exception when S/S and /R are both zeros. Then Q and /Q will be both 1s. But that's unusual. So once we have this, we can go to a D flip-flop and try to think about how to make a D flip-flop. First of all, we have an SR latch, and then we got two NAND 2 gates. So we'll go pick up two NAND 2 gates. Duplicate, there we go. And we also have just a regular negation gate. So make it narrow, there we go. We got 2 input pins and 2 output pins. So 2 input pins, 2 output pins. All right, and we'll label everything so that we know which one is which one. And the labels of the input pins are D for data, and then EN for enable. The NAND 2 gates are named N1 and N2. So we got N1 and we got N2. The SR gate, the SR latch is just called lowercase SR by itself. And then the 2 output pins are just like the before. One is the non-negated output Q, the other one is the negated output. I think we can use /Q too, so that's kind of cool. We can use /Q in LogicSim, but when I do it in the pseudocode here, the N here is basically the slash. It means negated Q. Okay, so now we need to look at the connections. And let me see if I can look at this way. Oh, that's cool. We can do it that way. So when you look at the connections, the data pin connects to both. Okay, I think this is mislabeled. Okay. If we look at the enable pin, oh, this is NQ, by the way. No, that doesn't make a lot of sense. Did I mislabel the pins?
The knot.
Yeah, there's a.
Oh, there's a not, and okay.
It's hidden.
Lower in your code.
Yep. There we go. This is AND itself. Okay. Oops. Not B. And.
Maybe the alt, no.
There we go. All right. Now it starts to make more sense. Okay, so D goes to N1.in0 directly. So that would be, so these 2 pins are connected like that. It goes to the input of the negation gate, and then it goes to N.out goes to N2.in.1, which is this one. So, oops. So this one goes here, and we tap it here. There we go. And then the enable pin goes to both of the input pins of the NAND 2 gates. Okay. And apparently I only did half of the jobs of connecting the pins. I'm missing the other half. So the other half is here. This is the SR latch. So whatever is coming out of this one, this is the Q, and this is the NQ. Okay. And then this one is just connected to set, and this one is connected to reset. Okay. Everything is in blue because I turned off simulation. So there's no simulation right now. Okay, but this is a D flip-flop. So now we have the truth table again. Okay, we want to know what's going to happen for the 4 possible cases. And let's see how we can do this. I can put this one here and do it over there. Okay, does that work for you guys? Okay, all right. So now we want to look at the 4 possible cases. So we want to look at D, E, N. These 2 are inputs. So we have the 4 possible cases for the inputs, like that. But we also want to track, maybe, I don't know. Do you want to track the nodes that are internal? The internal nodes are this one and this one. Those are the internal nodes, and so is this one. Do you want to track the internal nodes? Yeah, why not? So N.out is the output of the negation gate. We also want to track N1.out, the output of the first NAND 2 gate. Oh, you cannot see that. Let me see if I can move this. Have some empty space. I know, we can do it like that. That leaves more empty space. There we go, the other side. There we go. And then we have, I need to write smaller. Okay, scratch N.out, N1.out, and then we got N2.out, and then we have SR.Q. Okay. So SR.Q is really the bottom line. /Q is kind of like a byproduct. For the most part, we don't really care about it. Okay. All right. When En is a 0, what's going to happen? When you look at a circuit, when En is 0, it goes into the input of both N1 and N2. So what is that going to do? N1 and N2 are NAND gates. If you have a 0 as one of the inputs of an AND, what is going to happen to the output? It's going to be false for a regular AND, but if it's an AND, then it becomes 1 for the outputs. So this alone is going to cause N1 out to be a 1, N2 out to be a 1. I don't even care about N1 out. Okay, it's not important to me. Because if N1 out is a 1 and N2 out is a 1, what's going to happen to the SR latch? It's maintaining its state. Because it's 1, 1, it's 1 for /S, we're not setting. It's 1 for /R, we're not resetting. If we are not setting nor resetting, what is it going to do? Retain the state. Does that make any sense? So that means SR.Q is NC, no change. Okay? And that applies to this one too, because it's the same scenario. N.out, I don't even care, because we know for sure that N1.out and N2.out are both 1s, and as a result, there's no change to the output of the SR latch. Is that okay? What about the second row? Okay, the second row is having D as 0 and En as 1. So this one, we do have to be a little bit more careful. So N.out itself is going to be what? N is just the negation of D. So this is going to be a 1. Okay? So if that is a 1, what's going to happen to the circuit? This one is a 1 already, and En is a 1 as well. So N2 out is going to be a 0. So N2 out is a 0. What about N1 out? Enable is on, D is a 0. But since at least one input is a 0, the output is going to be a 1. So N1.out is going to be a 1. But when you look at this from the perspective of the SR latch, what is it going to do? It is a reset, because you're absolutely right. So /R of the SR latch is a 0, which means we are resetting the SR latch, which also means Q is going to be 0. Very good. So it will change to a 0. If it's not a 0 before, it is now a 0. If it was a 0 before, then we don't have a change. Is that okay? The last row is having the enabled NA turned on and data being 1. So when you have enable turned on, this input is going to be a 1, but since data is a 1, this negated 1 is going to be a 0. So N2 is the one that guarantees to have an output of 1 in this case. So N2 has an output of a 1. What about N1? D is 1, En is 1 as well. When you have two 1s going into the input of a NAND gate, the output is a 0. Okay? So N1.out is going to have a 0 here. And N.out, by the way, is a 0. So what is this combination going to do? N1 out goes to /S, N2 out goes to /R. So what are we doing? Are we setting or resetting?
Setting.
We are setting, which means Q is going to be a 1. It is changing to a 1 if it was not a 1 before. So are we doing okay so far with this particular circuit? This is kind of like a 1-bit memory, because you have a way to say, oh, here's the bit, here's the value I want you to remember, and now remember it. Okay. So let's play with this circuit a little bit. We'll enable simulation, and so we can okay. That's because I turn on both at the same time, and this is an oscillation. It's having a little bit of an issue here. All right, so let's reset the whole thing. We'll turn enable to be a 1, and you can see how it is storing this 0. What happens when I flip this D to a 1 right now? Keeping En to be a 1, but changing D to from a 0 to a 1. What do you think is going to happen to this circuit? Nothing is going to happen to the SR latch, or does it change to this new specification right away?
I think Q and not Q are going to flip.
They're going to flip. You're absolutely right. Okay. So as long as En is a 1, whatever I specify in D is going to affect the SR latch. You see how the change of D is changing the SR latch right away. Okay. If I turn off enable, I can do whatever I want with D. Nothing happens. Is that okay? So that's why this label is called En, is enable. Okay, En stands for enable, and enable is not negated. If En is a 0, the device is disabled, it doesn't update. When En is a 1, then we say, yes, it is enabled, and whatever you specify in D immediately affects the result of the SR latch. Is that okay so far? With the D flip-flop, this is basically just a gated, what we call a gated gated D flip-flop, because the purpose of En is quote-unquote to gate the update.
What did D stand for?
D is data. It is whatever you want to store. And En is enable, which means, do you want me to store now? Do you want me to store now? You say yes, then it goes like, yes, now we go ahead and update the SR latch. But at the core, it is the SR latch that is serving as the memory device. The other devices, the other two NAND gates, are really just conditioning the inputs so that we have one bit, one input pin specifying what value do you want to store. And then the other input pin is specifying, do you want me to store? As opposed to the S and the R, which is basically asking, do you want to set or reset the input? Is that okay? Right? So once again, I missed a few lines of the node specification here. I will go back and fix it. And then section 5 talks about an edge-sensitive D flip-flop. This one is even more complex. Okay, so let's go ahead and just create a circuit first, and then we'll try to do some analysis and figure out what it does. So we have this, and let's draw this one. Well, I do want to run it, so let's do it in Logic. This is a clock sensitive D flip-flop. Okay. Alright, so we'll pick out the components that we need first. We have one pin called the clock, CLK, one pin called data, or D, and then we have two SR latches this time. So one is called S, one is called C. So we go back to SR latch. 1, 2. And then we have two NAND 2 gates. So we go to gates, pick out a NAND, change it to 2 input, and narrow. That's the first one. And then the second one, this is the second one, by the way. The first one has 3 inputs. So we go from 2 to 3 inputs. And now here comes the really, really obscure part, is how do we connect these pins? I think this time I got it right. Okay. Alright, so we got the, let's connect the clock and the data pins first. So the clock goes to the reset pin of, okay, by the way, the two SR latches also have their own names. This one is S, and this one is C. There we go. All right. So now we want to figure out, how do we connect all of these pins? Oh, there are 2 output pins that I'm missing here. So here's Q, and we'll just do Q because not Q is not really that useful anymore. Alright, so data pin goes to D2.in, so this one is easy. It just goes to the second input of the second gate. There you go. The clock, on the other hand, goes to S.R, okay, which is this one. It also goes to the other input pin of D1, the middle one in D1. Oops, in N1. There we go. This is N1. And this is N2. There we go. And then we have C.R, which is the output of C going from D1.out. So D1.out goes here. But it also goes one more place. Oh, D N1, sorry. I use D in this case, not N. There we go. So D1.out goes to D2.in1. Should be using 0 index, but I forgot to use a 0 index in this case. So we got D2.out goes to one of the inputs of D1, and there's one more thing connected to the inputs of D1. So D1.in0 is also taking S.nq, which is this one. What about C? C dot. Oh, I think I'm missing some connections here again. S.S is here, so it's D2.out. S2.out, which is this wire, also goes here. I'm going to cheat a little bit and look at the picture that I drew later. It's about the same thing. It's a little bit different, but it's very close. So we know the /Q is what also hooks up to S here. Okay. And then this connects here. There we go. All right. So this one is a little bit harder to analyze because you can see that there are quite a few more connections. But let me show you the effect first. So the effect of this one is we have a clock line. So the clock line, when the clock goes from 0 to 1, that is when the SR latch updates. So once it updates, I can change the data line all day long and nothing happens to the latch. Is that okay? If I change the data to be 1 and then I go for another 0 to 1 transition on the clock line again, the output changes again. But I can keep flipping the data line all I want as long as the clock is not in transition. You can change the data line all day long and nothing happens to the output of the SR latch. Is that okay? Let's do that one more time. So we'll try to store a 1 into Q again. To store a 1, you put a 1 into the data first, but you also need a low to high transition or a 0 to 1 transition with the clock in order to update Q. So we want to change it to 0 because changing from 1 to 1, you cannot see it happening. So this is the 0. The moment I change this 0 to a 1, it updates the output. But that's the only time it's updated. I can now change data and it doesn't do anything. Now when you look at this diagram, you can see why that is the case. Because I can change this all day long, but because this line here stays dark green or stays 0, it doesn't matter what data is, it's not going to affect the rest of the system. So you can graphically understand how it works, how it is not quote-unquote level sensitive. What if I want to store a 1? Okay, clock has to go back to 0, and then it's the transition from 0 to 1 that matters. Okay. Now it transitions and it updates. So once again, let's see what happens here. You can see no matter how I change data, it only changes one single node, which is this node here. Okay, this is the node that is changed when I change data. But all the rest, the other nodes remain unchanged. That's how it works. It's called edge sensitive. When the clock line, CLK, transitions from 0 to 1, at that very moment, the output of the SR latch C is going to update according to data. Are we kind of doing okay? Now, to analyze this circuit, one thing you can do is to say, okay, what if clock is 0? I can change data all we want and nothing happens. Why is that the case? Well, in this diagram, it's easier to actually visualize because I can click on one node. When clock is 0, the reset input of SR latch S is low, which means we are resetting the output. And as a result, /Q is guaranteed to be 1, and that turns out to be /S, which means we're saying we're not setting. Okay? But when clock is low, it is also fed to D1. D1 is a NAND 3 gate. Okay, has got 3 inputs. But as long as at least one input of a NAND gate is a 0, the output is guaranteed to be 1. But that output from D1 is going to /R. So when /R is a 1, we are saying we're not resetting. Well, hold on a second here. We're not setting and we are not resetting, which means the SR latch maintains its state. That is why when clock is low, you can flick data as much as you want and nothing happens to the SR latch. Okay? So the magical moment happens when clock goes from 0 to 1. that is the time when data is quote unquote sampled, and whatever data has is reflected in the output of SR latch C. Why does it work like that? Okay, so right now is a good state to talk about, because when I transition this clock from a 0 to a 1, let's see how or what changes is going to occur in this diagram. Okay, so just imagine in your mind right now. I'm not going to click it. We want to work this out mentally first, and then we'll click it. So at this moment, when CLK goes from 0 to 1, what is going to happen? What is it directly going to cause? Right now, it's connected to two things, right? Okay, let me click on the node itself so that we know how it is connected. Yep, go ahead. It's connected to /R, which is currently a low, right? What happens when /R goes high? Is it going to change /Q of SR latch S, which is the top? Is this /Q going to change as a result of that? No, it's not going to change, okay? Because it will maintain its state. What about the D1? When clock changes from 0 to 1, what's going to happen to D1? D1 currently outputs a 1 only because clock is a 0. So the moment clock goes to a 1, then we have all three inputs of the NAND 3 gate being 1s. What happens when all inputs of a NAND gate being 1s? The output is going to be a 0. So when the output goes to 0, which is connected to /R of SR latch C, what is that going to do to the SR latch? It's resetting. And when it resets, then the Q output is going to be a 0. Okay? So let's clock and figure out. Yep, that's exactly what happens. So now the question is, how come at this point it's no longer sensitive to the data? I can change data all day long and nothing is going to happen. When you look at data, it connects only to D2, right? And D2 is now outputting a 1. Why is it outputting a 1? It has got two reasons to output a 1. Okay, because all it needs is one of the inputs to be a 0 to output a 1, and now it has two reasons. If I change data from 0 to a 1, it has just lost one reason. But the other reason is still there, because the other reason is this other dark green wire connected to D2. So as long as that wire is still dark green, the output of D2 will remain to be a 1, which means I have isolated the changes of data from the rest of the gates. D2 is helping me to isolate that change. Okay, I can click it now. You can see visually, you can see how this change is completely localized to this wire. Nothing else is changed. So the other way around is a little bit more complicated. Let me change the output back to a 1 first. So to change the output back to a 1 from 0, you have to go through a 0 to 1 transition, like so. Okay? Now, why would changing the data line not do anything to the output, to the output SR latch, which we call C?
And one of the inputs is already 1.
Okay, so it will change the output of D2, right? Because at this point, D2 is outputting a 0 because both inputs are 1s. So when data goes from 1 to 0, D2 is going to output a 1. So this one connects to two different places. The first place it connects to is D1. Would that affect the output of D1?
Depends on the SR latch, right?
Depends on the SR latch. Okay,
Which
very
we
good.
know isn't going to be the same.
So let's analyze the SR latch first. Okay, so we click on the wire to look at where it connects to. It connects to /S. What happens when /S turns from 0 to 1? It maintains, right? Okay, so that means /Q continues to be dark green. But /Q also goes to D1. As long as at least one input of D1 is a 0, the output is going to be 1. So once again, we have isolated all the changes from the SR latch, this wire will change. So that wire will not even change because we are just asking you to maintain the state. But on the other hand, this wire will not change either. So /R of C does not change, /S of C does not change. The SR latch says, I don't see any changes. Does that make any sense? Now, I looked at this design about a year ago, when we changed the curriculum of this class to include this kind of logic. And I felt that this is really ingenious. I mean, this whole design to make it edge sensitive is really, really smart. I mean, I wouldn't be able to come up with this design. Do you see another SR latch in here? This is one of those, remember when you were a kid, they would ask you how many faces do you see in the picture? Yeah, but there's another SR latch. D1 and D2 are actually another SR latch, except D1, instead of only having 2 inputs, it has got 3 inputs. That's the only reason why it doesn't look like an SR latch. So the question is, can we replace D1 and D2 with an SR latch plus some extra ingredients?
Could you just do AND?
Yep, you can do a regular AND.
As one of the inputs?
Yep. So let's go ahead and see how we can change this one so that it becomes just SR latches and nothing else. All right, so we'll do the usual thing because I don't want to destroy the original. Copy. And, duplicate, even better. There we go. Okay, so what we want to do is to okay. So what we will do is we're going to take out these 2 guys and most of the wires. Control Z, selection tool. Okay, and then we take another SR latch and put it here. Okay. So when we put the other SR latch here, I think it's pretty clear that data goes to the reset of the other SR latch. Okay, that part is pretty clear. And then the internal wire from D2, the output of D2 to the input of D1 is already inside the SR latch itself. So that one doesn't need to be drawn. But when you look at the output, or this is the /Q of the second SR latch, it also goes to /S of this SR latch here. So this wire needs to be represented explicitly. Oops, don't need it to be that long. There we go. What about this one here? What is this node corresponding to? It is it's Q. It's really just Q of the new SR latch. It connects to /R of the other SR latch. What connects to the set portion? It'll be, okay, this one is already accounted for, so we have 2 additional wires. Both this one and this one serves as the set /S of the new SR latch that we're constructing. But we only got 1 pin. What are we going to do? Yep, we'll do another AND. So the reason why we can do this kind of stacking of AND, let me show you just graphically why we can do it. Okay. So you look at a 3-input AND. This is a 3-input AND. Is it the same thing as that? It is. It has to do with the associativity of conjunction. And because of this, we can now go back to our circuit diagram and go like, okay, we can just use a regular AND gate with 2 inputs. And let's make it not called D2 anymore. And we can use this to combine the 2 inputs into into the original D2. So 1 is coming from the output /Q, so it will be this wire.
Are you using an AND or a NAND?
This is supposed to be AND, not NAND. Thank you. I was trying to be lazy and just use a component already there. Okay, so this is 1, and then the output of this goes here. Where's the other one? The other one is the clock line, which is from here. So to make it look slightly nicer, we can, okay. There we go. All right. it still looks kind of ugly. Yep. Well, okay, let's figure out whether this continues to work or not. Okay, so we'll go back to simulation mode. It is a 0 right now. I want to store a 1. So first of all, we have to make sure that we can flick, the data line all we want when we're not transitioning. And then we want to check when we transition from the clock from 0 to 1, is the output updating? And the answer is yes. Okay, very good. And then we can see whether this should not make any changes. And this should not make any changes either because we are not seeing a transition. So we go back to 0, have clock go back to 0, and then go to 1. The output should change to a 0, and that works too. So yes, so these two designs are functionally the same. It's just that most of the time you don't see the use of 3 SR latches. You just see the use of a 3-input NAND gate and then the use of a 2-input NAND gate instead of another SR latch. Are we still doing okay so far with this? Yep. Okay. So right now, with this design, either looking at the top version or the bottom version, we have a clock sensitive or edge sensitive D flip-flop, which means you can specify the new data that you want to store as data, but it's not going to store it until you see a transition from 0 to 1 at clock. Okay? But we don't have the enable anymore. This one is edge sensitive, but it doesn't have the enable anymore. I cannot gate the update anymore. Okay? So how do we make it gated again? So for this part, you just have to kind of take my words for it. This is the gated version. Okay, you can see how it is kind of the same as what we saw before, except we have an extra input pin called EN, and then we also have an extra AND gate here to go to this R here, and then we have, instead of a 2-input AND gate for A2, we have a 3-input AND gate. To accommodate for EN, to go to A2, and also go to A1. Because EN, going to A2 and A1 means that when EN is a low, when we do not want to enable the device, when we don't want it to update, A2 and A1 will guarantee output zeros. When A1 outputs a 0 to R, it's going to reset, and /Q is going to be 1, so we are not setting anything in the final stage SR latch. At the same time, A2 would also output a 0. When A2 outputs a 0, SR2 is going to be set. When SR2 sets, the Q output, which goes to the R of SRC, which is the final stage SR latch, would also be a 1. Which means the final stage SR latch would just be experiencing 2 1s for the inputs, which also basically specifies no change. So enable being 0 turns off all the possibility to change anything, because that is the one thing that guarantees the final stage SR latch not to change anything. Is that okay? But we forgot one more thing. When you first start up a computer, the transistors are all kind of going in different states. There's no actual safe known state. So it would be kind of handy to have a way to zero the content of a D flip-flop and just say that when this pin is a 0, just reset the whole thing to 0. without actually storing a 0, because when you store a 0, it means the processor is running some kind of a program. But you need to make sure that all the internal states of the processor is known at a certain state before you start it. So it's a chicken and egg problem. You cannot use a program to initialize itself. So what do we do? This is what we do.
Is that a reason?
So we add 2 more gates. Okay, so O1, which is OR1, and A3 are added in this case. So when you look at O1 and A3, what are they doing? They're taking the usual thing. Okay, one is taking /Q of SR1, the other one is taking Q. The other one is taking Q of SR2, which were directly connected to SRC, which is the core or the final stage of the SR latches. Okay? But instead of having those wires connected directly to the final stage SR latch, now we have the gates. We have an OR gate that has a negation going to reset, which is active low. We also have an AND gate, A3, connecting to the same thing, but not negated. So what's going to happen when reset goes 0? Okay, let's track it down. When reset goes 0, it goes here. A3 becomes 0. What happens when A3 goes 0? The output of A3 goes to R of the final stage SR latch, and what does that do to Q? R is active low, which means when R is 0, we want to reset, and Q is going to be a 0. Is that okay? What is that going to do to O1? When reset is low, the negated version of reset is going to be a 1, and O1 is just maintaining whatever it has here. But this is an OR gate. With the OR gate, the output is guaranteed to be 1, so that means when reset is 0, we know for sure that the S input of SRC is a 1, and R is going to be a 0, which means we guarantee to reset the final stage SR latch. Is that okay so far? What if reset is a 1, which is usually the case? Then the 2 additional gates, they do not do a single thing, right? Because when reset is high, A3 is going to have a blah 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 and 0. Excuse me, and 1. Blah 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 and 1 is just maintaining that blah blah blah, because the 1 is the identity of conjunction. So no change to the original circuit from before. When reset is a 1, what is it going to do to O1, the OR gate? Okay, reset is a 1, the negation of reset is a 0, blah 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 or 0 is just the original thing, because 0 or false is the identity of disjunction. So that means by using the gates O1 and A3 the way we do it, when reset is a 1, it functions just like before. Nothing has changed. But when reset is low, then we actually reset the content of the final stage SR latch. Okay? I know the class, the other class is waiting outside, but since I wrote this already, we might as well take a look at this. Okay, this is basically the multi-bit version of a resettable, edge-sensitive, and gated D flip-flop. Okay, so we can use that term all semester long, or we can just call this an 8-bit register. And I think an 8-bit register is a little bit easier. It's an 8-bit register. It can store an 8-bit content. That's all it does. Okay, you present the 8-bit content you want to store in D. Make sure reset is high so you're not resetting the device. Make sure EN is 1 to enable the device. And whenever clock goes from 0 to 1, it will update all of these D flip-flops, and will also at the same time update the Q to be the content that you want to update. You want it to update to. So now we have the smallest memory device in the processor. It's called a register, otherwise known as a resettable, gated, edge-sensitive D flip-flop. Multi-bit version of that, yes. So that concludes the lecture of today. We'll come back and take a look at these again on Wednesday, and then next Monday is going to be our practice exam.
Can I ask you a quick question?
Yeah, go ahead.
Is define allowed in